All right, so we are recording. All right, we are now in probably one of the most important sections in chapter 8, Taylor and Maclaurin series. So you learned about power series and in section 8.5, and in section 8.6 you learned that certain functions could be written as power series. And sometimes, well, you learn that. But the methods of section 8.6 are the type of functions that can be written as power series in section 8.6 are there. It's somewhat restricted because it all relies on the fact that you can take 1 divided by 1 minus x and express it as a geometric power series. All the problems in section 8.6, the fact that we could write those functions as power series, stem from that result. Well, we want to have a more general way to express a function as a power series. And that's what Taylor and Maclaurin series are. So let's go here down a little bit. And first of all, we suppose that any function can be represented by power series. So a power series, if we were to write sort of the most, and maybe I have it highlighted here, but if we were to write the most general form, let's see, I think I'm going to have to keep it highlighted. Hold on. I think I'm going to have to keep that highlighted, actually. Hold on, everybody. Now I gotta figure this out. There we go. Yeah, so the function f of x can be written as a sum, an infinite sum of terms, with coefficients c sub 0, c sub 1, c sub 2, c sub 3, and so forth. And then there's an interval of convergence given by the absolute value of x minus a is less than some radius of convergence. This is just a general form of a power series. It's the most general form. And this form of the power series that you're seeing in the box that has the 1 on it there is only useful if we can figure out what, first of all, what a is, okay, and normally we know what the a value is that we want to use, and then also we have to be able to figure out what those coefficients are: c sub 0, c sub 1, c sub 2, c sub 3, and so forth. So if we could determine a, and if we could determine the coefficients, we can have a function f of x that's completely defined. So what they do in the problem is they say, okay, well, let's try to determine what the coefficients c sub n must be in terms of the function. Okay, so the function, if we substitute in x equals a in that equation above there, that equation 1, if we do that, then all those terms are going to drop out, right? If we let x equals a, all those terms are going to drop out. Okay, so maybe I can just show this on the whiteboard here. Hold on here. So, and let me get it down to 2-point font, that'll be fine. So f of x is equal to c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared plus c sub 3 times x minus a cubed, and so forth. Now, f of a, if we compute f of a, then we're substituting a for x, right? We're substituting a for x. See, there's a substitution.
So, Professor, we're substituting the x with a?
That's correct.
Oh, okay.
That's correct. And what happens here to all of these terms? What's a minus a equal to?
Smaller than r?
If you a minus a, well, it's just
Oh.
0.
Oh, yeah.
That's right, O'Kearney. Yeah, it's just 0. And so look, f of a is equal to c sub 0. In other words, we have found one of the coefficients. So we're trying to get a formula for these coefficients here. And now I know what the first one is. Okay, now what about c sub 1? What could we do there? Well, if we take the derivative of this f prime of f, then that would just equal the following. Wait, hold on. I have an error here. The derivative of a constant is 0. Derivative of x minus a is just 1. Derivative of x minus a squared is 2 times x minus a to the first power. Derivative of x minus a cubed is 3 times x minus a squared, and so forth. Well, what we can do is we can, in the derivative, substitute in a, x equals a. And if we do that, hold on. This is 2c2 times hold on here. This is 3c3 times a minus a squared, and we can keep going. What happens here? Those terms are 0. Oh, wow. So it looks like f prime of a is equal to c1. Now I know the second value, the second coefficient. I know what c1 is. So far, are we okay? All right. Well, let's keep going. Let's go back to the book. Let me ask you this. If I wanted to figure out what C2 was, how would I find C2? What would I have to do with the function?
Find the derivative of c1?
That's right. Well, I'd find the second derivative. That's right,
Yeah.
Susanna. And that's right. You mean, Clea, the second derivative? That's right. Second derivative of the function. All right, good, Susanna, good, Clea. So now I'll go back to the ebook. This is all in what I just showed you in the whiteboards in the ebook. But here's the second derivative. There it is. And if we put x equals a, we're going to find out that f double prime of a equals 2 times c2, or c2 equals f double prime of a over 2. And you see, we can keep So now we've determined what that third coefficient is, and we can keep doing this. You see, we can take the third derivative. We can take the third derivative, and then it'll turn out that that when we substitute in, let me just highlight this here. Yeah, when we substitute in x equals a into the third derivative, it turns out that the third derivative of the function evaluated at a just equals 3 factorial times c3. You see how in that third derivative, how factorials are building up? And so in general, then, well, c sub 3 would be the third derivative of the function at x equals a divided by 3 factorial. And you can keep going and going with this. There's a pattern. And the pattern is such that the c sub n for this general power series, I mean, the function has to be, it basically has to be continuous and differentiable, okay, over the real numbers, well, over an interval, but you know, it has to be basically a well-behaved function. But the coefficient, we can find a general formula for the coefficient, and it's the nth derivative of the function of a divided by n factorial. And so now we have then our power series representation. If we take our function and express it as that power series you see there, the coefficients are given by that formula. The c sub n is the nth derivative of the function evaluated at a divided by n factorial. Okay, this is one of the most important results in mathematics that you're learning. Okay, remember that first day? Remember that day when you got your driver's license and how happy you were? Remember that day? How many felt, man, this is a big day for me, getting my driver's license? Okay, Daniel remembers that. Mandy remembers that. Well, this day is just as important. It is. It really is, because this is incredibly important what you're learning. So look, we can then express the function as the power series that you see there. We can express the function as the power series that you see there. And this is called a Taylor series. Okay, this equation 6, I'll go down a little bit. The series in equation 6 is called the Taylor series of the function f at x equals a, or about a, or centered at a. When we have a Taylor series, we have to identify what we are expanding the Taylor series about, what value of a. Now, many times we want to, well, are there any questions before I move forward here? We're going to get to a few examples for sure. Yes, Claire.
Professor, my question is, what's the difference between this summation and the one we just saw before?
Well, it's the same summation. It's the same summation. What you saw before, let me go up here. This was the summation. Let me just see here, hold on. I can't. This was the summation that we started with, right? We said, let's suppose we can take a function. The function has to have continuous derivatives, okay? Has to be differentiable, so high derivatives exist, higher derivatives. But the function, we're gonna write the function as this power series in the gray box there. But in order to utilize the power series, we need to determine what the coefficients are. See, in the power series that you learned, like in section 8.5, for instance, you knew you didn't have any coefficients you needed to figure out. But here, this is a general form of a power series. For it to be useful, we need to determine the coefficients. Well, we determine the coefficients for that general power series, where we set the function equal to a power series. And the coefficients we determine here in theorem 5, we determine those coefficients. You see there the C sub n part, this part here. Hold on, can I highlight? Yeah, we determine those coefficients. There they are. And so now we just then put those coefficients in the formula there, right? In the power series and we put those coefficients in, and that's going to give us then what you see here. Okay, so that's a very general formula, very general formula. It's a Taylor called the Taylor series formula, and incidentally, when a equals 0, if a equals 0, we have, that's a special case. The special case a equals 0 for the Taylor series gives us what's called a Maclaurin series. Okay, so what we want to do, and this is now section 8.7 will be on your final exam, but what we want to do is we want to be able to write, functions as Taylor or Maclaurin series. Maclaurin series is when a equals 0. So let's go to an example. Let's get right to an example here. Okay, let you copy this example down. We're going to find a Maclaurin series for this function, cosine of 3x divided by 4. Okay, let me give you a moment to copy that down. Yes, Mandy. Question. Oh, no problem. No problem. Yeah, Mandy, I've not made up part 2 of the exam. Part 2 of the exam, the questions, of course, take longer. So probably there would not be 30 questions on part 2. Okay. All right. No problem. No problem. You're welcome. All right. So you know, we want to express this function, the cosine of 3x divided by 4, as a Maclaurin series. Now let's remind ourselves from the ebook. This is a Maclaurin series. That is a Maclaurin series. So take a look at it. What do we need to find in order to create a Maclaurin series? What do we need to find for the function to get the terms of a Maclaurin series? The terms of the Maclaurin series are found by computing what? How do you find the terms of the Maclaurin series? There they show the first 3 terms of the Maclaurin series.
we need the derivative.
That's right. That's right, Clay. We need the derivatives. And in order to get the formula, we need to determine the pattern for those derivatives. Okay, there's a pattern. So just like, remember this problems with sequences when you had to figure out formulas for a sequence? Well, we need to figure out formula for the Maclaurin series. So, okay, let's go here then. So, okay, we're going to have to take some derivatives of this particular function. And we're going to have to take enough derivatives until we figure out the pattern. So let's go to the next page where I have things worked out here for the solution. What I did was I found the first four derivatives. The first four derivatives. Okay, that's what we have here. And then for all those derivatives, I evaluated those derivatives at a equals 0. Okay, so let you copy up to here. Let me know if you have any questions. Okay, so I think things are pretty well spelled out here. Again, you know, I'm going to try to figure out what this series is, this Maclaurin series is for this cosine of 3x divided by 4 function. So, you know, I go out 4 derivatives, and I get my values here, and then I substitute the values in to the Maclaurin series. Okay, so here's where I substitute the values in below here. All right, are there any questions so far? Yes, Susanna.
Why are you putting, where did you get the factorial?
Oh, the
Dividing by
factorials. The
factorials.
factorials come from the formula, the Maclaurin series formula.
Okay. Okay, I see. Cool. Okay, thank you.
Okay. And the reason another question was asked, why am I putting 0 in everywhere here? Why am I computing the function its derivatives at a equals 0? A equals 0 because we're doing a Maclaurin series. Maclaurin series means a equals 0. Okay, good questions. Let me see. Jonathan and Susanna, very good. So, okay, we get here, and I'm wondering what the summation is. What's the summation formula? Well, I don't have enough information quite yet. Well, I have enough, but I want to just, I want to do another step. Okay, so may I go to the next page? Is everybody good? Okay. Let me ask you, let me ask you this before I go to the next page. Blow this up a little bit here. Expand on that. Do you think like if I wanted to put in a few more terms, okay, what would go in front of x to the 5th power if you had to guess? What would the next term be in front of x to the 5th power? Right, that's right, Jasmine, it's 0. It appears that the odd terms, the terms that have the odd powers, x, x cubed, x to the 5th, and so forth, have a 0 in front of them. Whereas the terms with the even powers, 1/4 is 1/4 times x to the 0, right? So x to the 0, x squared, x to the 4th, and x to the 6th, it appears those would be non-zero terms. So under x to the 6th, like x to the 6th, we're going to have a 6 factorial in the denominator. But then, based on, would that term be positive or negative, by the way? In front of like the next term. So this goes on and on. But x to the 6th power, would that term be positive or negative? First term was positive. Next non-zero term was negative. Next non-zero term was positive. So that means this next term should be, what do you think, positive or negative? Should be negative. That's right. Maybe I can be more. Let me go to the whiteboard here. Let me write down what we have here. So okay, so we have a 4th. Okay, we have a 4th. Minus 9/4 over 2 factorial times x squared plus 81/4 over 4 factorial times x to the 4th. If we wanted to know the next term, of course, there's going to be a 6 factorial there. Oh, but next term is going to be minus. Let me see. Yeah, well, what I'm doing is I'm just writing down the non-zero terms. I'm writing down the non-zero terms. Good note, though. Good note. No problem. What do you think the term's going to be here? Something over a 4th, right? Because look at these two terms. You had a 4th, well, and then you had 9/4, 81/4. What do you think's what number's going to go here, you think? The numerator is 1, 9, 81. What do you think is going to go next? That's right, 729. Okay, so I'm just trying to kind of help you get a feel for this. We need to get the pattern. Okay, let me now bring this up. Let me bring this up. Actually, I have this also in the solution. So let me bring that up. Let me bring that up here. So this is where we're at. Let's go to the next page. And I write it out in quite a bit of detail, and then this gets us to here. So you have to get enough terms written out so you can see what the pattern is. And the formula, you see, because like that 1/4 there, we could write that. What I'm doing here is I'm looking here. That 1/4, well, we could write it as 1/4 times x to the 0th power all over 0 factorial. And you can see that the general formula then for the power series is what you see there. The series n equals 0 to infinity of -1 to the nth power times 3 to the 2nth power times x to the 2nth power over the 2n factorial. 3 is 3 squared, right? 81 is 3 to the 4th. 729 is 3 to the 6th. So it's 3 to even powers. That's 2 to the nth power. You see? That's our Maclaurin series. So just like in section 8.6, the homework, where you had to take a function and find out what its power series is, and there would be like usually multiple choice. Same kind of thing here. So now we have Maclaurin series for the cosine of 3x divided by 4. And that's nice, but again, that's great, but we have to ask for what x values is this true. We need to find the interval of convergence. Of course, if we have the interval of convergence, we can get the radiance of convergence. Yonatan, yes, question.
How did you go from the first section to the second section where you have something on the top, 1 factorial, 2 factorial, 3 factorial, 4, 5, 6, into 4 times 2 factorial, 4 times 4 factorial, 4 times 6 factorial?
Oh, okay, sure. Let's take a look at this. Let's take a look at the -9/4 over 2 factorial. Okay, let's take a look at that. So -9/4 divided by 2 factorial is the same.
Oh, I didn't read that right. Never mind. Yeah, no, you just flipped the fraction. Okay, thank you. Sorry.
No problem. I can write that as -9/4 over 2 factorial over 1. That's -9/4 times 1 over 2 factorial. And that's how we, well, yeah, that's how we get this here. Okay, very good. Are there any other good questions? All right, well, so now you see, because we didn't use remember section 8.6, those problems were based off of the 1 divided by 1 minus x formula, and we were able to establish a interval of convergence off of that. Being that basically said the problems in section 8.6 were based off, we found power series representations of those functions based off of a geometric power series. And the geometric power series, based on what our common ratio was, we could establish an interval of convergence easily. Here, we don't have that. So we have to use the ratio test to establish what the interval of convergence is. So basically, we have a power series like we would have in section 8.5, and we have to use the ratio test to establish the interval of convergence. And if we need to test the endpoints, we need to test the endpoints. So that being said, let's use the ratio test to figure out the interval of convergence. Okay, so clearly in this problem, the nth term, okay, the nth term is right here. This is the nth term, a sub n. So let's go to the next page and do the ratio test. Okay, so remember the ratio test, you have here the nth term of the power series. And to get the n plus first term, you just replace anywhere you see an n with an n plus 1. And all right, a fraction divided by fraction means you take the top fraction and multiply by the reciprocal. I'm going to let you copy here, but that gets us down here. Let me give you a moment to catch up. All right, so now that we have this, we group together like terms. So I'm really trying hard in my work to show you as many details as I can. A lot of times, textbooks, this is an excellent textbook, but it is. But it's standard in textbooks that they don't show this much detail. Well, I'm happy to fill in the blanks for you. So, okay. So now, how do we handle this 2n plus 2 factorial? This 2n plus 2 factorial, that comes from, 2 times n plus 1 is 2n plus 2 factorial. I write that as 2n plus 2 times 2n plus 1 times then 2n factorial. Nice things are going to happen. The 2n factorials are going to simplify out, and that's going to give us then this ratio, this limiting ratio. Well, it's the ratio, and then we're going to take the limit as n goes to infinity. But please let me know if you have any questions. I think you've done the ratio test enough with respect to power series that this math should be understandable. But nevertheless, we put, there's a parenthesis there, right? So now we take the absolute value of this expression, and the negative goes away, and all the other parts of the expression are positive, so we can drop the absolute value. And as n goes to infinity, this denominator here is going to go to infinity. And that means the rational, the fraction 3, which is 3 squared times x squared divided by the 2n plus 2 times 2n plus 1, that's going to approach 0, which is less than 1 for all x. For all x. So no matter how big the value of x is, whatever it would be, the denominator, that's going to go to infinity. So this this power series, I'm going to say this the right way, the interval of convergence is going to be from negative infinity to infinity, because the ratio test says that the limiting ratio is going to be 0, and 0 is less than 1 for all x. The factorial, Clea, well, what happened is I rewrote the 4 times 2n plus 2 factorial. I rewrote that as 4 times 2n plus 2 times 2n plus 1 times 2n factorial. And the 2n factorials canceled, you see. The 4's canceled as well, incidentally. 4's drop out as well. Okay, very good, excellent. So, okay. Are there any other good questions? Absolutely beautiful. Franklin, how about you? Any questions, Franklin? Nihat, how about you? Any questions? Okay, good. All right. Let's see. Avery, how about you? Any questions? All good. All right. Okay. Well, then, so this means then the interval of convergence is negative infinity to infinity. Essentially, what you're saying is this. You're saying that the cosine of 3x divided by 4 is equal to this power series. And that's good everywhere for all values of x. So you actually have a function that equals its power series for every value of x. And you see, sometimes it's more convenient to write, to work with the power series of a function rather than the function itself, particularly if you can't, like for instance, integrate the function. You saw some of that in section 8.6 in some of the problems. So that is a nice example from section 8.7 here. We just saw a nice example dealing with Taylor series. So I want to do another example with you, but I want to give you a little break here. So are there any questions before I stop the recording? Okay, let me stop the recording then. Very good. Let me just see here. Yep. Excellent.